A rectangular plate of 15 mm thick made up of brittle material as shown in figure. Only for brittle material you have to apply the stress concentration factor. The ratio of the stress at 3 mm diameter hole to 5 mm diameter hole you have to find out. That is the ratio of the sigma max at 3 mm diameter and sigma max at 5 mm diameter you have to find out. Since we have a circular hole, so we have value of kT is fixed for circular hole, that equal to 3. To find out the value of sigma max at diameter equal to 3, we'll consider here a section. Let's say this section is AA. So we'll first calculate here what is the nominal stress at section A, and then we'll calculate the maximum value at section AA. For this entire plate, the width is constant, that equal to 25 mm, and we have thickness is H is equal to 15 mm. So we'll make a cut here and we'll develop the figure at section AA. So this one is a rectangular plate of width equal to 25 mm, and here we have very small hole of 3 mm diameter, and then we'll show the thickness that equal to 15 mm. So this area as well as this area will resist the given force and it will develop a nominal stress. So together here this area will be equal to, we have width equal to W. Let's say this diameter equal to D1 and this diameter equal to D2. So we have W minus D1 multiplied by the thickness equal to H, and we have force is equal to 20 kilonewton. So we can calculate here the nominal stress is equal to force divided by area. That is same as equal to force divided by W minus D1 multiplied by H. Force will take in Newton, that equal to 20,000. So we have 20,000 divided by width W you have to take as 25. Diameter D1 you have to take as 3 mm, and the thickness you have to take as 15 mm. So this much is the nominal stress produced at section AA. This value is equal to 60.61 megapascal. And we know the theoretical stress concentration factor, size of the hole doesn't matter. Only for circular hole we have kT equal to 3. So we have maximum stress at section AA. Let's say this value equal to sigma 1. It is not a principal stress, just I am denoting it sigma 1 is equal to theoretical stress concentration factor multiplied by nominal stress, and theoretical stress concentration factor is 3 and nominal stress is 60.61. So this value of sigma 1 is very close to 181.82 megapascal. So same analysis you have to carry out at section BB, which one we have taken at diameter equal to 5 mm. So one more time we'll cut it and we'll develop the figure. So we have the width is shown here, that equal to 25 mm. This time we have slightly larger hole, that equal to 5 mm, and then we'll show the thickness which is perpendicular to the plate. So this one is representing the thickness. So this hatch area will resist the given force. So we'll produce the normal stress. This area is same as equal to W, that is the width minus diameter D2 multiplied by H. So here we have nominal stress produced at section BB will be equal to force divided by area is W minus D2 multiplied by thickness equal to H. We have same value of force equal to 20,000 divided by width here will be equal to 25. So we have uniform width. Diameter D2 is equal to 5 and we have thickness H is equal to 15. So in this case we have nominal stress produced at section BB will be equal to 66.67, that will be megapascal. Corresponding maximum stress produced at section BB will be equal to kT multiplied by sigma nominal, which is same as equal to 3 multiplied by 66.67. Let's call this value equal to sigma 2. 3 multiplied by 66.67 is close to 200. megapascal. What we require the ratio of the stress at 3 mm, that is sigma 1, to 5 mm diameter. So in this case we have sigma 1 divided by sigma 2 will be equal to 181.82 divided by 200 is close to 0.91. A flat plate is subjected to tensile load of 10 kN. Permissible stress in the plate, that is the maximum value of the stress, you have to take as 100 megapascal. The stress concentration factor of the whole section is given this time is 2.1. So don't use your formula. You take the value of Kt equal to 2.1. The thickness of the plate we have to find out. Width is given as 45 mm. Diameter is given as 20. So first of all, you have to cut at the section which is passing through the hole. So at this section, first of all, we'll find out nominal stress, and we have given the value of maximum stress sigma max, which is present at the top here. So this one is sigma max, will be equal to 100 megapascal, and theoretical stress concentration factor you have to take as 2.1. So again at this section we'll develop the figure. Thickness we have to find out. So let the thickness will be equal to h. So we have a plate of width equal to 45 mm. Then we have a circular hole, and this one is the thickness. So this area will resist. Actually it is same area. This is a freehand. So this area will be same as equal to W minus the diameter of hole multiplied by thickness h. So first of all, what we'll do here, we'll calculate the value of nominal stress. So we know the Kt is equal to sigma max divided by sigma nominal. In this case, we have sigma nominal will be equal to 100 divided by Kt, that equal to 2.1. So nominal stress produced in this case is approximately equal to 47.61. That will be megapascal. Now this area which is resisting the force F will produce the nominal stress. So we have nominal stress will be equal to force divided by area is W minus D multiplied by thickness h. Already we are knowing the value of nominal stress, that equal to 47.61. Force is equal to 10 kilonewton, is 10 into 10 to the power 3, and whole thing is divided by the width, that equal to 45. Circular hole of diameter equal to 20 multiplied by h. Solve this equation, we will get the thickness h is close to 8.4 mm. A large uniform plate containing a rivet hole is subjected to uniform uniaxial tension of 95 megapascal. The maximum stress in the plate you have to find out. We have given here the width, that equal to 10 cm, and we have given the diameter equal to 5 mm. But this value you provided is itself will be equal to the nominal stress, because in this numerical the value of force is not given. So this value will treat as a nominal stress, and no value of Kt is given. So theoretically we have Kt will be equal to 3, which is same as sigma maximum divided by sigma nominal. So this one is only valid in the case of circular hole, and you have to use this value if the value is not provided. Otherwise you can read the value from the graph. So sigma max will be equal to 3 times of the nominal stress, which is equal to 95. So 3 into 95, that will be equal to 285 megapascal. So this type of questions are normally asked in a GATE examination. In the case of static loading, we have introduced the stress concentration factor for the axial loading as well as the shear loading. These stress concentration factors are neglected in the case of ductile material but are considered in the brittle material. So notch can be a hole or a groove or a fillet and abrupt change in a cross section or any disruption to the smooth contours of a part. So there is a geometric discontinuity and therefore there is a stress concentration. The notches of concern here are those are deliberately introduced to obtain the engineering features such as O-ring. For that one you have to do the semicircular groove, then fillet on the step shaft to reduce the stress concentration, fastener holes, etc. So it is assumed that the design engineer will follow a good design practice and keep the radii of these notches as large as possible to reduce the stress concentration factor. The geometric, that is the theoretical stress concentration factor Kt, and the normal stress KTS for shear stress already we have discussed. These factors give an indication of the degree of the stress concentration at a notch and having a particular contour. And we can calculate the value of sigma maximum from the theoretical stress concentration factor, and we have sigma max is same as equal to sigma nominal multiplied by value of Kt or value of KTS. Depend whether we have a axial stress or we have shear stress. Whereas for dynamic loading, we need to modify the theoretical stress concentration factor by a fatigue stress concentration factor. So actually we are not introduced to the fatigue stress, but since we are in the stress concentration, I will introduce this term. Fatigue stress will introduce in the fatigue loading. So if Kf represent here the fatigue stress concentration factor for normal stress, which one is a ratio of a fatigue limit of a unknown specimen divided by the fatigue limit of a Notch specimen. Fatigue stress concentration factor for normal stress is given as the fatigue limit of a unknown specimen to fatigue limit of Notch specimen. Both these definitions are valid if we have a axial loading or we have a bending. In the case of shear stress, we will define KFT, which is called as fatigue stress concentration factor for shear stress, is defined as the fatigue limit of a unknown specimen to the fatigue limit of known specimen. Both in this case our load will be a torsion. So in general, the fatigue stress concentration factor is defined as the fatigue strength of a notch-free specimen over the fatigue strength of a known specimen. So even though it is effectively defined as affecting the material property strength, and it can be used as a stress increase in the nominal stress in the case of dynamic loading. So just like KT or KTS for static loading, the fact that the sensitivity is reduced when going from static loading to dynamic loading. And that is from the static to fatigue analysis comes mainly from the fact that the notch stress affecting the fatigue life is not the maximum stress at the notch, but instead it is the average stress acting over a volume of a material close to the notch. Adding to this, any crack that is initiated at the notch will be growing into the region with the stresses that are much lower than the stress concentration. The theoretical stress concentration factor and the fatigue stress concentration factor are related by the notch sensitivity, which is represented by Q, and it is defined as a ratio of the fatigue stress concentration factor minus 1 divided by the theoretical stress concentration factor Kt minus 1 in the case of axial loading. And the same value of the notch sensitivity can be defined for the fatigue stress concentration factor for shear stress, that is KFT minus 1 divided by the theoretical stress concentration factor for shear, that is KTS minus 1. So this one you have to define for shear. The value of Q ranges here from 0 less than equal to Q less than equal to 1. So minimum value is 0 and the maximum value of the notch sensitivity equal to 1. So materials have different sensitivity to the stress concentration, which is referred as a notch sensitivity Q. In general, the ductile material, the less notch sensitive, and for brittle material it is more sensitive. So if we solve here the equation of a notch sensitivity, which is defined as the fatigue stress concentration factor for dynamic loading, to Kt, which is a theoretical, that is a static stress concentration factor. In that case, we get the value of Kf will be equal to Q into Kt minus 1 plus 1. And this notch sensitivity varies between from 0 to 1. Once you calculate the value of Kf, which one is a fatigue or dynamic stress concentration factor, then the nominal dynamic stress for any situation is to be increased by factor equal to Kf. stress will be given as Kf multiplied by sigma nominal. Same story that we have done for static loading. So when the value of Q is equal to 0, if the value of Q is equal to 0, we have value of Kf is equal to 1. So there is no effect of dynamic stress concentration factor. And in this case, the nominal stress is same as our dynamic stress, that is sigma is same as equal to sigma norm, that is nominal stress. And if we take the value of Q is equal to 1, and if you put the value of Q is equal to 1, then minus 1 and 1 will be cancelled and Kf will be same as equal to the theoretical stress concentration factor. That is, the entire effect of geometric stress concentration factor is felt if your value of Q is equal to 1. Now the theory about the calculation of Q was developed by Neuber, so we're not going to discuss that. We'll only introduce here the Notch sensitivity, which is Kf minus 1 by Kt minus 1. Similar to Kf, we can calculate here Kft. So value of Kft will be same as equal to Q multiplied by the theoretical stress concentration factor for shear minus 1 plus V of 1. So Notch sensitivity and the fatigue stress concentration factor will discuss more detail in the case of fatigue loading. One simple numerical will take based on the Notch sensitivity. For a beam, stress concentration factor for static load is equal to 1.35. For static load means the value of Kt is given, that equal to 1.35, and the stress concentration factor for fatigue load is represented by Kf is given as 1.3, and we need to find out the Notch sensitivity. So the Notch sensitivity Q is given as the fatigue stress concentration factor minus 1 divided by theoretical stress concentration factor for static loading. So we have value of Kf is equal to 1.3 minus 1 divided by the theoretical stress concentration factor is 1.35 minus 1. That is, we have 0.3 divided by 0.35, which one is very close to 0.857. For a gate examination, you just prepare the definition of Notch sensitivity. Step shaft has a theoretical stress concentration factor of 1.9. So we have given the value of Kt is equal to 1.9, and we have given the Notch sensitivity that equal to Q is equal to 0.9. Value of Q is always between 0 to 1. The fatigue stress concentration factor of the shaft, that is the value of Kf, we have to calculate. So we'll use the same formula for Notch sensitivity, which is Kf minus 1 upon Kt minus 1. This time we have Notch sensitivity is given as 0.9. Fatigue stress concentration factor Kf we have to find out, minus 1 divided by theoretical stress concentration factor is 1.9 minus 1. Solve this, you will get the fatigue stress concentration factor Kf, which one is very close to 1.81. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.